We'll quickly revise what we studied in the last lecture, and then we'll go on to some new topics, new variations of gradient descent. Firstly, we had started with looking at the surface plots and the contour plots, and we said that both of them are representing the same thing, but the surface plot is in 3D, the contour plot is in 2D. We have also plotted these arrows. What do you think these arrows are representing? These arrows are showing the gradient vector at the respective places, right? So it's important to note that the gradient is defined at a particular point. And if you look at the entire structure, entire plane, you're talking about the gradient field. So the gradient also gives the direction in which the function will increase at the maximum pace. In this case, for this function, we had calculated the gradient as the vector of the partials, which is the partial with respect to x and the partial with respect to y. So we get 2x 2y vector. We had also looked at optimization algorithms in a general sense. We had said that the goal is generally to optimize or maximize or minimize a function subject to some constraints, but for the purposes of these few lectures, we are looking at the unconstrained setting, which is we are not giving any constraint. We looked at one particular cost function, which was the which was the linear regression cost function, which was the sum of squares of the residuals. So it's a function of theta, the parameter vector theta, which is y minus x theta transpose times y minus x theta. And we said that our goal is to find that particular theta which minimizes this function. We said that we'll be using gradient descent as our optimization algorithm. So there were a few important attributes of gradient descent. First, it is an iterative algorithm, which means that you start off with some initial value and then you improve upon that value. It's a first order approximation, first order optimization algorithm. Can someone tell me what you understand by first order? Why is it called a first order approximation? Because we are only looking at the first order terms from the Taylor series. We are not looking at the Hessians, we are just looking at the gradients. So the main algorithm is as follows. You initialize theta to some random value. You compute the gradient of the cost function. So we have a minute more, after which we'll have to lock the classroom. So if any of your friends ask you, you can tell them. Initialize theta to some random value. We compute the gradient of the cost function at theta, which is del f evaluated at theta. And for iteration I till convergence or till the number of iterations elapse, we update theta I as theta I minus some constant known as alpha times the gradient evaluated at theta of I minus 1. So we said this whole derivation we could have come with respect to the Taylor series, where the expansion we are trying to approximate any function with the help of a polynomial. So the polynomial is given as, so the important thing is that we are doing this derivation around a point x naught. The polynomial is f of x naught plus the gradient of x minus x naught plus the second derivative, so on and so forth. Can you close the doors? No, you can actually lock it. Can you lock the door? Rishabh, can you lock the door? So we said that the vector form, we can also use the vector form of this expression where the second derivative is replaced by the Hessian, the first derivative is replaced by the gradient vector. We had looked at few simple examples. Importantly, through this procedure we had found out that the delta x which we want to move, when we want to change, so when we want to move from x to delta x, such that the functions f of x plus delta x is lesser than f of x, we figure that the delta x is minus alpha times the gradient evaluated at x naught. So, this was the important thing which we found out, which motivates the use, which brings us to gradient descent. So, we had also very briefly looked at the effect of learning rate. If I keep the learning rate very low, then our optimization will proceed very slowly, or we will not be able to get convergence. So, here you can see that we start off at 2, we go to 1.96, 1.92, 1.88. The growth is the rate of decay or approach towards the global minimum. The local minimum is very slow. If we had chosen the learning rate to be a very high number, in this case 0.8, so you can see that we move from this blue to the orange. We have skipped the optima, then we move to the other side, then we move on to this side again. So, we are repeatedly crossing the local optima and we are overshooting. So, this phenomenon is known as overshooting, where we are moving on the other sides of the optimum in respective iterations. Of course, over time this will still converge, but it is a very noisy convergence. Whereas, if we had kept the learning rate to be very high, in this case 1.01, you can see that we move from the blue to the orange to the green to the red. In this case, this behavior is known as divergence. Right? So, we have looked at 3 different kinds of behaviors. The first is very slow convergence, where the learning rate is very slow, very low. The second is the learning rate is high, so we have overshooting, but it's still converging. And this case is known as divergence, where we'll keep on. So, we wanted to minimize f of x, but now we'll end up not minimizing f of x. Each successive iteration will give us higher values of f of x, of the functional value. Can you folks start off with the attendance? We'll have 3. In this case, the fourth case, we are looking at an appropriate learning rate of alpha equal to 0.1, and you can see that it's nicely converging. In a few number of iterations, it will converge. We had looked at a few common terms. The loss function, which we said is defined with respect to a single point. How much loss do I get if I predict it wrongly? For example, squared loss, which is the prediction minus the ground truth squared. Then we have the cost function, which is a more general term. In the case of linear regression, our cost function is defined as the sum of the loss functions over the training examples. So, this was also one of the questions in your quiz. So, the mean squared error, which we commonly use in linear regression, decomposes over the examples, but there are other metrics which do not decompose, like for example F1 score. And then the most general term in these 3 is the objective function, which is any function which you want to optimize. We had also looked at this example briefly, but I think this is important to again go over it. So, we have y equal to theta naught plus theta 1 x is the function you are trying to learn. You initialize theta naught theta 1 to 4, 0, choose a step size of alpha equal to 0.1, and you want to run this for 2 iterations. The first thing you will get is you will calculate the errors with respect to the different points, epsilon 1, epsilon 2, epsilon 3. You calculate the mean squared error, which is summation epsilon I squared over the number of examples you are calculating over n. So, in this case I have just evaluated the function. Generally you may or may not need to do this. So, you get a function which is linear in theta, quadratic in theta, and independent of theta. It has 3 types of terms. Right. So, we can calculate, in this case I am just calculating in a more general way. I can calculate the gradient, I can calculate the partial with respect to theta naught and calculate the partial with respect to theta 1. So, in both the cases I am able to write this in the terms of epsilon i's, and the second case epsilon I and xi's. And then we will just have the simple gradient descent update rule, theta naught equal to theta naught minus alpha times the partial with respect to theta naught, and theta 1 equal to theta 1 minus alpha times the partial with respect to theta 1. So, these were some calculations I had shown. We basically go from 4 to 3.6 for theta naught, and theta 1 goes from 0 to minus 0.67, right. So, if you notice, our theta naught has reduced by 0.4, and theta 1 has increased in magnitude by 0.67. Does this look like the correct behavior or wrong or no? If we are optimizing a function, do we expect the theta i's to reduce or no? Okay. We expect the function value to reduce. We don't expect the theta i's to reduce. Can you just go and open them? Can you open the door, Jaidev? So this particular observation is important because sometimes we make a mistake on it. The first and the last time you're allowed. Next time it will be closed sharp 8:35. Okay, this is settled. So we'll take that question offline. We'll take that later. Chirag, can you close the door? Chirag, can you close the door? In the next iteration, we'll take theta naught to go from 3.6 to 3.54, and theta 1 will go from minus 0.67 to minus 0.55. The important thing is to note what is happening in this contour plot space and the actual fit space. So I started with a value theta naught equal to 4 and theta 1 equal to 0. Right? So that's what I plot. And if you can notice these ellipses, these are showing the loss surface, and you can notice that this is the optima. X equal to 0, y equal to 1, or theta naught equal to 0, theta 1 equal to 1. Why is this the optima? Because that's the data set that I specifically curated. So for this data set, you can see that the intercept is 0 and the slope is 1. So theta naught equal to 0, theta 1 equal to 1 is what you're trying to learn, expecting to learn from this data set. But we started off at this point, theta naught equal to 4, theta 1 equal to 0, and we are somewhere here in the surface. So we expect that we'll make some progress towards this optima, right? So we'll keep on taking steps towards this, and this is the line fit which we have obtained thus far. Theta naught equal to 4, so it's 4 plus 0, 4 plus, why is this line like this? Over the different iterations, you will now notice very carefully, just look at this point, which is theta naught theta 1 point. So if you notice the point has moved slightly below, you saw that theta naught became 3.6, theta naught became 3.6, and theta 1 became minus 0.67. The next iteration, so you should just look at it as an animation, and you will also see how the line fit will keep improving. The blue line will keep getting closer to the actual line. Right. So if we go over it again, in each iteration we are progressing towards the optima, and the line fit will keep getting better. I've shown only for a few iterations. If you repeat this procedure for a few more iterations, you will see that the blue line and the orange line will coincide. Right. So that's the main objective here. Any questions thus far? Okay. So there are two commonly used terms in the literature for optimization algorithms. One is iterations, the second is epochs. Oftentimes they're confused, they use interchangeably, but there is a big difference between them. Does anyone know the difference between iterations and an epoch? Okay, have you heard of the two terms, iterations and epochs? Sorry? So iteration, the way I am defining it for this purposes of this lecture is each time you update the parameters of the model, each time you update theta, you say that you have done one iteration. Each time you have seen all the set of examples, you call that as an epoch. Right? So for the cases of simple gradient descent which we have thus far seen, is iteration and epoch the same thing? When do you update? So in gradient descent, your loss or the objective function, can you notice that it has to have all the components, it has to have the loss computed over each and every data point, right? So therefore you compute the gradient once you have seen all the data points, and that's when you update the parameter as well. So therefore for vanilla gradient descent, iterations and epochs mean the same thing. Right? Epoch, you've seen all the examples. Iterations, when you're updating the parameters. And this becomes more clear when we look at the stochastic version of these gradient descent algorithms. So thus, in gradient descent, we can have a simple for loop structure like this. You start off with a data set, initialize some theta for epoch in 1 to capital E, where capital E is the number of epochs. I predict y hat equal to predictions for x comma theta, right? Or typically also call this the forward of x comma theta when we look in the neural network kind of world. So important thing, I am passing the entire data input features x, the parameters theta, and I get my y hat, which is of the same size as y, which is n. Right? So this predictions is over n examples. Right? So therefore for each epoch I am seeing all the examples. I compute the loss, which is the loss function evaluated over y and y hat, and I compute the gradient. Importantly, the gradient is evaluated over a certain point theta, right, which is this current value of theta that I have, and then I have the regular update rule, theta equal to theta minus alpha times the gradient of the loss evaluated at theta. Any questions in this? Right. So you start with some value of theta, you compute your prediction over the entire data set containing n data points, you compute the loss over the entire n examples, you compute the gradient of the loss, you evaluate the gradient of the loss at the current value of theta, and then you update theta as the previous value of theta minus the step rate learning rate times the gradient of the loss evaluated at the previous value of theta.
So now x need not be full rank.
Sorry?
Now x need not be full rank.
Now x need not be full rank, right. You will observe that for the cases of normal equation you required x transpose x to be full rank matrices, whereas for this method you don't really need that. Whereas the other variant, which is very commonly used and which is one of the reasons why we can do very large scale learning, is stochastic gradient descent. The important difference is that you still want to run it for some number of epochs. Firstly, you can shuffle the data set, typically done, not necessarily required, but typically done. Then if you notice, for the data set for iteration I in 1 comma n, right? In each epoch, I am now looking at each and every example in the data set separately, and I am updating my parameters. So let's go over the previous one again. In this, how many times am I updating the parameter vector theta? Capital E times, right? How many data points do I see in each epoch? N. Now let's look at the stochastic gradient descent. Here, for each epoch, how many times am I updating the parameter vector theta? N times, where n is the number of examples. And I have total E epochs. How many parameter updates have I done? E into n. How many passes of the entire data set have I done? Capital E, right, which is the number of epochs. So that's the way I've specifically written in this way. In each epoch, you go over n examples, and each of the n examples for stochastic gradient descent, you update the parameter vector theta, right. So for each example x of I, the ith data point, you calculate you figure out the prediction y hat of I, you compute the loss with respect to only a single data point, right, and then you compute the gradient of the loss evaluated at the previous value of theta, and then you do the theta update. Any question in this? We do shuffling to prevent some cyclical behavior. Okay. So we have seen two extremes. One is known as full batch gradient descent or just vanilla gradient descent, where the number of epochs is E, and in each epoch you update the parameters once. So you have updating the parameters once you have seen all the n examples. The stochastic gradient descent is on the other extreme. You update the parameter vector theta for each example, right. So therefore the number of updates to theta that you do in stochastic gradient descent is much higher than in gradient descent for the same number of epochs, right. In this case, it's a factor of n. So in between, we have another variant, which is mini batch gradient descent. So I've tried to give you the pseudo code, which is the way you may also end up writing this code, these different variants. So what we say is that instead of now treating one single data point to update the parameters, we will be now using a small batch of data to compute the loss and then update my parameter vector theta. So pretty much similar as previous, but I make some batches of the data, which is, so let's say if my data is 100 points, I may make batches of 10. So I have 10 batches of 10 data points each. And for a batch of examples, I compute my prediction, I compute the loss, compute the gradient of the loss evaluated at the previous value of theta, and then I do the update. So what happens if B, here is the number of batches, what happens if B equal to capital N? What variant is this? Stochastic gradient descent, right? Your number of batches is equal to the size of the data. What happens if capital B equal to 1? Full batch gradient descent, you have a single batch over which you are computing the loss. So we have seen these variants in vanilla gradient descent, or what is also typically known as the full batch gradient descent. We update the parameters after going through the entire data set, all the examples. So thus we generally get a smooth curve for iteration versus cost. How does the cost reduce, or how does the objective reduce with respect to the iterations? But this takes more time because you have to compute the gradient over all the examples. Whereas for stochastic gradient descent, we'll update parameters after observing every single data point. So we will end up having some noisier curve for iteration versus cost versus iterations, but it will be quicker. Let's work through an example for this in your notebooks, after which I think you'll get a lot of clarity, and we can see then appreciate the difference between the two algorithms. You have y equal to theta naught plus theta 1 into x. We want to be using stochastic gradient descent, and the initial values of theta are the same, 4 and 0. Step size is 0.1, and I want you to run for one epoch, which means 3 iterations. I've also purposefully just shuffled the data, right? So can you tell me what is the value of theta naught and theta 1 after the first iteration? Let's work this out in our notebooks. If needed, please talk to your neighbors. Feel free to talk to your neighbors, discuss, and then come with the solution. If you're not able to start with the first step, just write y hat equal to what plus what, theta naught plus theta 1 into x. Just write that for the first example. You now know the y hat, you also know the y. You can calculate the error for the first data point, then square it up. That should give you a start for this. Does anyone have an answer? What? 3.2 and minus 1.6. Just check your calculations once again. You're probably missing a factor, or you have an extra factor of 2. Okay, let's go over the solution. We had y hat equal to theta naught plus theta 1 x. That's the first step you should always do in this such simple cases. Then write the error for each of the data points. For the first data point, what is y hat? Theta naught plus theta 1 into x. What is theta naught? 4. And what is theta 1? 0. Or in general, if you write error for the first data point is the ground truth y minus y hat. So, y hat is theta naught plus 2 into theta 1 because x was 2. Similarly, epsilon 2 and epsilon 3 you can calculate in this way. Now, all you want to do is to calculate, just look at the first data point to update my value of theta naught and theta 1. My first data point corresponds to a error or loss of 2 minus theta naught minus 2 theta 1, the square of this quantity. And if you are to compute the loss with respect to this, so by the way, this is the 3 loss surfaces which I have plotted. Right. So this is with respect to the first data point 2 2, this is with respect to the second data point 3 3, and this is with respect to the third data point 1 1. Right. Can you notice firstly that they are not exactly identical? Right. The surfaces are similar. Will they have the exact same minima or not? Will they have the exact same minima? Or one minima would suffice, would work for all of them, right? We'll give a loss of 0 for all of them, right? Which is corresponding to the relationship of theta naught equal to 0 and theta 1 equal to 1, right? For all 3 of these examples, that holds true. But if you broadly see the loss surfaces, they're not exactly the same, right? That's because the error functions which we had for them, they are different. They are 2 minus theta naught minus 2 theta 1 squared, 3 minus theta naught minus 3 theta 1 squared, and 1 minus theta naught minus theta 1 squared. So they're different, because of which the 3 error surfaces which you're getting is different. But for the first gradient update, we will be looking at only the first error surface, right? With respect to this error surface, I have now calculated my partial with respect to theta naught and partial with respect to theta 1. Here I have done for a more general case of xi and yi. So it comes out to be the 2 times yi minus theta naught minus theta 1 into xi into minus 1, which is 2 times epsilon I into minus 1, and with respect to theta 1 it's 2 times epsilon I into minus xi. Right. So previously, if you had noticed, for the case of gradient descent, we'll have something similar, but what additional thing will we have there? So here we have 2 times epsilon I into minus 1 and 2 times epsilon I into minus xi. For gradient descent, if you notice, we had a summation term here. Right? Because we were computing the loss with respect to all the examples xi, yi. Here we are computing the loss with respect to a single example in stochastic gradient descent. So therefore, here we had 2 over n, taking the mean over the n examples of summation epsilon I into minus 1, and here we had 2 over n summation epsilon I into minus xi, whereas now we have two epsilon I into minus 1 and 2 epsilon I into minus xi. Right. So therefore, you can always go from one of the more general to the more specific case, and knowing these values, can you now compute the value of theta naught and theta 1 after this iteration? So now I've given you the gradient. Can you now tell me the new value of theta naught and theta 1 after one round of iteration update? You already know the value of xi and yi and epsilon I. To calculate epsilon I, you have to substitute the value of theta naught and theta 1, and xi you already know. Okay, I've just completed the calculations. So I get 4 minus 0.1, which is the learning rate step rate, into 2 into then we had epsilon I into minus 1. So epsilon I was y minus y hat, your y was 2, your y hat was 4 plus 0 into x. So it comes out to be 2 minus 4 minus 2, and if you do the entire calculation, you will get 3.6. Similarly, for theta 1, you get the initial value of theta 1, which was 0, minus the learning rate into 2 into epsilon I into minus xi. Xi was 2 here, and if you do the entire calculation, you will get 3.6 and minus 0.8. Does everyone follow this? And similarly, we can then do for the next iteration. Importantly, for the next iteration, your epsilon I would be and xi would be updated, right. So in the first case, our xi was 2 and our error was computed with respect to the first example 2, 2. For the next iteration, we will compute the error with respect to 3, 3, and for the next one, we will compute with respect to 1, 1. So iteration 2, we compute with respect to the 0.33, and the next value we have is 3.96 and 0.28. And finally, for the third iteration, we will be using xi equal to 1. So we get 3.3 and minus 0.368. To verify that whatever we have done is correct, we can also just run through the notebook. Okay. What do you think F1, F2, F3 here mean? These are the individual loss functions with respect to the ith data point. So F1 is 2 minus theta naught minus 2 into theta 1, right, and the square of that. So this is exact correspondence to what we had here. Right. So 2 minus theta naught minus 2 theta 1, the square of it, and that is what we have, 2 minus theta naught minus 2 theta 1 squared. Similarly, F2 and F3. So I have computed the different loss functions. I start off with theta naught theta 1 to be 4 and 0. And firstly, I am just showing you how you have created these different contours. Then importantly, I compute the gradient of the function f1 evaluated at the initial values of theta naught and theta 1. Here I am using x naught y naught to indicate theta naught theta 1, and I get del x and del y. I compute x1 equal to x naught, the first value of theta naught, minus alpha into del x, and similarly y1. So after this update, okay, I should have just run the entire notebook. Right, so this is the value that we had obtained. Importantly, here I am just using f1. In the next iteration, I do the same thing, but I use the next data point corresponding to which I have the next loss function f2. So I had got 3.96 and 0.28. After that, I will go to f3, my third loss function, or the loss function corresponding to the third data point, and I get 3.3 and minus 0.368. Right, the entire structure is the same, just that the input arguments and the function which I am calling is different. What is the next step after this? What should I do after this? We will start with the next epoch. So now we have seen one epoch, we have seen 3 iterations. Now we go to the next epoch. So once we have gone through all the n examples, we go to the next epoch. We can again shuffle the data, and after that we repeat the same procedure for the n data points. Okay. So the reason we can use stochastic gradient descent instead of gradient descent is based on the following slides. It's a slightly difficult topic if you've forgotten what bias and variance means, but if you remember those definitions, this should be fairly easy to get. So I'm saying the stochastic gradient is an unbiased estimator of the true gradient. Can someone tell me what you understand by this statement? So here we're talking in terms of not of a model, just of the gradients. Depends on what you call as the model, but forget model for now. We're talking in general about estimators. So there the model was an estimator. So you had a function. So when we're talking about decision trees exhibiting high bias, we had a true function and we had an estimator for that function, which was our decision tree model, and that was exhibiting low or high bias. In this case, the true quantity of interest is the true gradient, and our estimator is the stochastic gradient. Stochasticity generally refers to some randomness, some noise, etc. Yes, there was some other answer. Yes.
Expectation of stochastic gradient is the true gradient.
Expectation of
The stochastic gradient is the true gradient.
Okay, excellent. So that's the definition of unbiased estimator. So an estimator is unbiased if its expectation is the same as the true value which you're trying to estimate. Right. This is based on some excellent blog post by Florian Hartmann, which is this nice blog post. So it's pretty much borrowed from here. So let's say that we have a data set containing input output pairs of xi, yi's. We have n examples. Now we can define our overall loss as 1 over n, the loss computed over the individual data points, and then the sum of the losses, right? What kind of a, so here also you can see that the loss is decomposing over the n examples, right? So we can now have this individual loss or the penalty component to be some squared function, let's say just the squared loss, which is, so if we take this to be the squared loss, then our L of theta is mean squared error, right? Mean squared error means you look at the mean, you look at the error which is squared. So mean of the squares of the error, which is the loss function which we have used here, right? Now we can compute the gradient over the loss function, right? So it might be, why don't you write in your notebooks the gradient of this loss function and then see if you can simplify that expression. So you have to find del of L evaluated at theta, or nabla of L evaluated at theta, using this general form. You don't need to use this form, you can just use the first form and try and see if you can get some simplification out of this. The simplification I am looking is, can you move the gradient operator within the summation? Think of it, if you can do that. Okay, so let's go over the solution. We'll define the true gradient, capital, so nabla of L, to be the gradient evaluated over this entire expression, which is 1 over n summation I equal to 1 to n loss of this entire term. But we can now move this gradient operator within the summation. Why can we do that? Because the linearity of the gradient operator. Does everyone understand the linearity of the gradient operator? If not, if it seems like a complex term, you can simply take two functions, f1 of theta and f2 of theta. And you have to find out the gradient with respect to f1 of theta plus f2 of theta, both of them as functions. You can verify that if you find out the gradient with respect to f1 and find out the gradient with respect to f2, you add the two gradients, that would be the same as finding the gradient over the sums. Right? So, what you are saying is that the gradient of the sum is the same as the sum of the gradients. Right? Gradient of the sum is the same as the sum of the gradients, and because of which we can write it in this particular fashion. Right? So, here what we are saying is that we can compute the gradient of the loss with respect to every data point, and then I am just averaging over. Right? So, therefore, the gradient of the loss or the true gradient is the average of the gradients computed over individual data points. Right? That is the consequence of this writing, and that is where we now come up with the estimators. Right? So, when do we typically try and estimate some quantity? Why do we try and estimate the poll results? Because we don't know, we don't have access to the ground truth, the sample is huge, the population is huge, so therefore you get a sample, and from that sample you are trying to compute some characteristics. Right? Similarly, for the case of when we are doing some machine learning problem, if we had access to the underlying physical model perfectly without any unknowns, we should just use that, but we don't know that. So, therefore, we come up with an estimator for the underlying data distribution or the underlying function which we are trying to learn. So, therefore, we will say that let's assume we don't have access to the true gradient, right, or the true gradient is too expensive to compute. So, that is also when we use approximations or estimations, right. So, you can calculate the true gradient perfectly, but it is very, very expensive to do. Why would it be expensive to do? Why is the calculation of the true gradient very expensive? You need to? So, the differentiation is there in both the methods, gradient descent as well as stochastic gradient.
If there are very large amount of data points, then the time complexity will increase.
Okay. So, let us take a simplifying example. Let us say you have a data set which is 2 GB, right, and your RAM is 1 GB or your memory is 1 GB. What would you do? Can you fit the data in one chunk? No. So, if you can't fit the data in one chunk, you will not be able to compute the gradient of the entire data, right, because you can't fit it in memory. Of course, there are variants to this, but that is the general theme. When we do not have enough memory, we can't even compute the true gradient. So, therefore, what do? If you can't compute something exactly, you try and compute an estimate for it, right. So, we have looked at an extreme variant of the estimate, which is to use just one data point to compute the gradient in stochastic gradient descent. So, what we are saying is that we want to estimate the true gradient using a subset of the data. We have looked at two variants of this. One is mini batch gradient descent and the extreme version of which is stochastic gradient descent, right. Is this different from I am trying to figure out who will win the next elections? I do not have access to the entire data. That comes only after the counting is done. So, instead I use a subset of the data. I do something known as exit polls, right. Using the subset of the data, I try and estimate my quantity of interest. And sometimes it works out, sometimes it doesn't. In this case, stochastic gradient descent, it will exactly work out in average because of this property of unbiasedness, which we'll come to in a second. So we said that for SGD, we'll use a single example to compute the lossy or the noisy version of the gradient. Right? So these are some terms you will hear a lot in machine learning. You have a true quantity of interest, a true estimator, and then you'll get a noisy estimator or an approximate estimator. So let's say that we use a single example, x comma y. Now we can compute the estimate of the gradient using a single example as nabla of this L tilde. So tilde here is referring to the fact that it's an estimator, is the gradient to compute over the loss over the single data point, right. So here in the previous case, we had the gradient, the true gradient was the gradient of the loss calculated over all the data points. Now we have said that in stochastic gradient descent, we have randomly picked up one data point x and y from the data set, and we compute the estimation for our gradient as the gradient over the loss over this single data point, right. So the measure which is known as bias for a estimator x tilde, where the true estimator is, where the true value is x, is given by this bias of x, which is defined as the expectation over the estimator x tilde minus x, right. Okay. So why don't you use this definition? You should just write this down in your notebook for a second. Bias of x equal to expectation over x tilde minus x. And use this as your noisy estimator and show that this noisy estimator or the estimated gradient that you get from SGD is unbiased estimate for the true gradient. So first we are looking at this problem mathematically. After 3-4 minutes, we look at this geometrically, which should be easier, but first I just want you to try this out mathematically. You have to just plug this value of delta L tilde in the expression that I have given you. You have to find out the expectation over this. Again, feel free to discuss with the neighbors. The bias of
X or X tilde.
So bias of x tilde. This is the bias of x. And bias of the noisy estimator. So before you write anything on pen and paper, one important question you may want to answer is that whenever we calculate expectation, right, we calculate over a certain quantity, right, over a certain kind of randomness. What is the randomness that we're discussing here? Sorry? It's on this slide itself. The source of randomness is over this slide itself. If you understand that, you have the answer. Sorry? Shuffling of variables, or the fact that we have said that let us take a sample x, y from what data set? From the total data set that we have, right? So you have randomly picked up one data point from the data set. So therefore, when you have to calculate the expectation, you have to calculate it over any possible data point that could have been picked from the data set. So that is what you need to do now. How many have been able to show that this is an unbiased estimator? Okay, good. Does this estimator, so those who have been able to show, does this estimator have zero variance? It is unbiased, but does it have zero variance or not? Okay, how many have been able to solve this now? Okay, let's go over the solution. Our expected value of the estimated gradient is you compute the expectation over the data points n from the set of examples, right? So you write down this value, which is your estimated quantity for any data point x comma y, and you calculate the expectation over all the data points xi comma yi, which you could have got from the data set, which means you sum them up, sum of this quantity over all the xi yi pairs from the data set and divide that by n. That is exactly what we are doing. So sum of the noisy estimates or the gradients computed over the individual data points xi and yi, you average them over the n data points, you get this quantity 1 over n, the gradient over the sum of the losses, which is the same as your gradient evaluated over all the data points. Right? Is this becoming clear? So what is the consequence of this? Sorry? The bias is 0, but what do we do with that? If the estimator were not unbiased, would we be using stochastic gradient descent with that confidence? No. So then the true gradient cannot be estimated via the stochastic gradient. It will show some bias, but in this case we can. So therefore, as a consequence, we can use SGD wherever we want to use GD. Right? So that's the important question. Whenever we talk about estimators, we have the bias and the variance trade-off. Right? This is an unbiased estimator, but it exhibits some amount of variance. And that's what a lot of optimization folks are working on. Can you come up with better estimators which reduce the variance and keep it unbiased? So now let's try and look at this geometrically. Even if you didn't get the previous one, I would highly encourage you to focus and try and get this one, because this is more interpretable in nature. So let's say you have a data set containing n data points. You can obtain your y hat over the n data points. Let's say that this is the loss surface over your n examples, right? This loss surface is the same as in motivation as to, so same as to what I had shown when we were solving the regular gradient descent. Right? So if you notice here, we have a single loss function, a single loss surface, right? Which is what I am telling now, showing now. This is the loss surface over the n examples, right? This is now using full batch gradient descent. You can compute the loss over all the n examples and you can create this error surface. Let's say that at some time t you were at this point, then we can compute the gradient of the loss at that theta, which would try to take you towards the minima, right? I have just drawn it for representation, so don't look at it literally in terms of the length of the vector, but the direction is towards, it's going to take you towards the minimum, right? So this is the loss, so this is the gradient of the loss computed over all the n examples, right? So what did we do here? Let's repeat. We took all the n examples, we computed the loss over all the n examples, we obtained a single loss surface. Once you have obtained a single loss surface, if you are at any particular point theta, you can compute the gradient with respect to the loss, right, at that point theta, which gives you this single vector theta, which gives you the single gradient vector, right. Let's now see if we were to instead use stochastic gradient descent, in which case we iterate over all the n examples, right. If we iterated over the different examples, I had shown this previously that we will get different error surfaces for each data point. Why is that? Why do we get different error surfaces for each data point? So, for each data point, if you noticed, the error surface for the first data point is epsilon 1 squared, for the second is epsilon 2 squared, for the third is epsilon 3 squared. Each of them is a different function. As a consequence of which, and we've also seen this in the notebook, right? We have three different functions. So here it's more explicit. We have three different functions. If you plot the error surfaces over the three functions, they will look different, right? So therefore, I have plotted these three different, in this case I have just drawn 3, in general you will have n. So I have therefore put dot dot to show that this is the loss surface computing with respect to the first data point, with respect to the ith general data point, and with respect to the nth data point. So they can all be very different. And now if you take the same value of theta 0 and theta 1 across the 3 points, and the next step is you compute the gradients with respect to each of the loss surfaces at the same point theta 0 and theta 1, you will see 3 different, in this case I am showing only 3 different gradient vectors, right, shown in green. What do you conclude from these 3 gradient vectors? Does this give you any hint towards where we are going? So if we used all the n examples, we get a single loss surface. Then we can compute at any value of theta, we can compute the gradient vector, right? We get a single gradient vector. What gradient vector do we call? What gradient vector is this one? True gradient, right? That's the definition of the true gradient. The gradient computed over the loss, which is evaluated over all the data points, is our true gradient. Whereas, what are these 3 different gradients? This is one estimate of the true gradient, this is another estimate of the true gradient and this is another estimate of the true gradient, where each of the estimate is done over single data points. So, in this case I have capital N estimates of the true gradient. If I am to now just plot these one over the other, you can notice that the true gradient is shown in the red color. The individual estimates of the gradients are shown in the green color. Let me just get rid of all the background to make it simpler for you. This delta L or nabla L is the true gradient. This nabla L1, nabla Li, nabla N, Ln are your noisy estimates or your estimates for the true gradient. If I just consider this data point theta and I draw the directions of the individual estimates for gradients, how many lines do I expect to see here? Capital N corresponding to the n data points. Now, these are the gradients of loss for losses with respect to different points, different data points. Now, if I, what do you mean by an expectation over the individual gradients over the n data points? It's just the vector mean over these, right? So, what is the vector mean of these? It may be something like this, right? If I take the mean of all these vectors, maybe it's something like this, just drawn in illustration. It's the expectation over the individual gradients or the expectations over the gradients which were calculated for a single data point, and I have the gradient with respect to the whole data which is coinciding with this, right. Red one is my true gradient. What I am saying is that if I look at the gradients evaluated over the n data points, take the expectation over them or just the vector mean over them, it gives me a single vector now, which is the expected gradient. This is the same as the gradient which I had got if I had used all the data points, right. So, since both of these are coinciding, what kind of an estimator do I have via stochastic gradient? It's an unbiased estimator. There is no gap between these two vectors. If there was any gap between these two vectors, it would be a biased estimator, right. So, we have looked at it from two perspectives, one just math, just follow the derivation, the second geometric, which I believe is much more interpretable. Now, this estimator is unbiased, but can you see that it has variance? If you had picked up one data point, maybe this is the value that you had got. If you had picked up any other data point, maybe this is the estimate that you would have got. On average, you will get the correct value, but because you could have picked up any point from the set of training data points, you would have some variance. In this case, you can see the variance over this space, right. So, therefore, we are seeing an unbiased estimator having some amount of variance, and that is what I was saying a few minutes back. The goal is to try and reduce the variance. So, then you will have a better estimator going forward. Any question in this? Let's run over some simple examples to show you this in action. So, this plot is saying that if you stochastic gradient with a constant step size will converge very quickly to the neighborhood of the optimum, but then bounce around a lot. So, you can, let me make the step size fairly small. Right. So, can you see that firstly it is converging very quickly to the neighborhood, right. Initially it starts from here, very quickly comes to the optimum. It does not bounce out a lot initially, but after that it seems to be bouncing a lot. Why do you think this is happening? Use what we just said a couple of minutes back in terms of the unbiasedness, in terms of the high variance. So, the second point you can explain with the variance, right. If you had chosen data point 1, maybe it says that the gradient is in this direction. If you had chosen data point 2, maybe it says the gradient is in some other direction, because of which you will see a lot of bouncing around here. As you circle through the different data points, it will keep hopping around, right. But initially it shows a very quick convergence. Why is that? Sorry?
Initially, when it is calculating error, that is very high as compared to it is when it is so close to the optimum.
That is true. Initially, when you are very far from the optimum, the error is very high, and as a consequence of that,
Because initially all the vectors of all the individual points are pointing towards that optimum.
yes, excellent. So initially, wherever you start off with, whichever data point you pick up, it's very likely that they'll all point fairly similarly in the main direction, in this direction of the global optimum, right? When you're very, very far from the point. When you get very close, then you'll see the different data points correspond to different direction vectors. That's why you see a lot of variance, right? So therefore, it makes a lot of sense to be using stochastic gradient descent, at least initially, right? Because you don't need to go over all the n examples to update my value of theta when I am very far away, because all of the data points are giving you some roughly equivalent value addition. What they also show in this case is that instead, if you use some decreasing step size, so decreasing step size means that initially you had a step size of alpha. For the second iteration, let's say it's 0.99 alpha. For the third iteration, it's let's say 0.99 square alpha. So that's a geometric reduction in alpha. You could also have a linear reduction in alpha. Let's say alpha, the first iteration is alpha 0.2, the second is 0.195, then 0.190, 0.185, so on and so forth. So if you reduce that alpha, you will have lesser of the bouncing nature, you will quickly reach the optimum. Right. You will not have a lot of bouncing. Initially, anyway, it doesn't matter much. There are other variants to it which we will not cover. We may ask them in the assignment, which is which is based on similar ideas, that can you use some momentum term, etc. Seems to work well. Okay. Any other questions on stochastic gradient descent method? Okay. So we'll then very quickly breeze through the next topic, which is when we're trying to find out the time complexity of the different algorithms. I'm assuming that all of you are reasonably well versed with finding time complexity of matrix operations. So when we have the normal equation, so if you remember, our x was n dimensional, n data points, d dimensional, so n cross d matrix. The question I'm posing to you is, what is the time complexity of solving this normal equation? Theta hat equal to x transpose x inverse x transpose y. Can you calculate this in terms of the order notation, big O notation? It has to be something in terms of n, d, n and d. How do you go about this? So let's say that you have to first compute x transpose x. It's a matrix product. Can you figure out the time required for that? Then you have an inversion operation. How much time does that take? Then you have a x transpose y matrix vector product. How much time does that take? And then you have to multiply it to again a matrix vector product. How much time does that take? So you have to do these calculations, and then you'll see why it doesn't scale very well. The simplest way to solve this is to write down the dimensions of each and everything you're using here. Write down the dimension of x transpose, write down the dimension of x, multiply these two matrices, see what amount of time it will take.
Sir, it could also depend upon the order in which we are doing it.
It would depend on the order.
Because in DSA2 we saw something like matrix J.
Yes. In this case, it's relatively simple, like you'll have only two variants.
How is inverse calculated?
The inverse is of a n cross n matrix is n cube. Let's assume that. Okay, I'll walk over this solution. X is n cross d, X transpose is d cross n. If you have to multiply a matrix d cross n with n cross d, it requires d square n operations. Does everyone know this? If not, just work it out with a very simple example. Look at the number of multiplications and the additions you'll have to do. Inversion of a d cross d matrix takes d cube. X transpose y is a matrix vector, so you can think of that as d cross n times n cross 1. That will be, so the simple way to remember this is you have d n and n into d. So the common attribute or the common size occurs once, and you'll have this and this occur. So if this was, let's say, a into b and b into c, then the time complexity would be abc. So d cross n with n cross 1 would be d into n into 1, so dn. And then X transpose X inverse times X transpose Y is, X transpose X is a d cross d matrix, and this is a vector, d cross 1 vector, again a matrix vector product, which is d squared. And if you overall look at the complexity, add all of these terms, you have d square n, d cube, dn, d square. D square n is always greater than dn, so you just keep the d square n term, and d cube is always greater than d square, so you just keep those terms, so therefore you have d square n plus d cube. That's the time complexity that you get. There are other variants which we will discuss in the next class for gradient descent and other variants. And in the next class or the class after that, we will also solve movie recommendation problem. So we will try and recommend you to watch some movies, and we will see how that is related to the linear regression and the gradient descent methods you've learned. Thank you.